Welcome back one last time to the fifth and final video in our rational function series, where we learn to graph these rational functions with all of their asymptotes and intercepts and end behaviors and local behaviors. There's one last sort of weird caveat that we need to talk about with these, and this is the perfect example to do it with. I'm not going to waste any time explaining why it's a perfect example. I'm just going to start graphing it. As usual, I'm going to start by factoring. The top is going to factor into x minus 4 and x plus 1. The bottom should factor into x minus 1 and x plus 1. And already, hopefully, we have seen exactly what it is that makes this thing special. The special thing about this example is that it simplifies. Once you factor this, you realize two of these factors are the same, and those factors cancel. None of the other examples we've done have had this thing where pieces cancel. You can only cancel entire factors from the top and the bottom. Something I haven't really talked about yet. You can't cancel terms. It's very tempting to try and cancel these x squareds. But right now those are terms. There's other things being added and subtracted to them. Terms never cancel with division. Only factors. Factors, entire factors can cancel. And these entire factors match. This x plus 1 and this x plus 1, those match. So we can cancel those out, and then we're left with a very simple, extremely nice, extremely easy looking x minus 4 over x minus 1. Kind of like the first example we did, where it's just a linear thing over a linear thing. Nice and straightforward. Except when we cancel these, the factors cancel, but we need to preserve the domain restriction. The reason that we are preserving the domain restriction that these things would otherwise cause is this. Imagine choosing numbers for x. If x is 4, then this term would be 5, or this factor would be a 5, this factor would be a 5. 5 over 5 cancels. Those cancel, they're done. It's nice. If x is 99, then this is 100, this is 100. They factor, you're done. It's nice. If x is negative 142, then this term is negative 141, and this factor is negative 141, and they cancel, and you're done, and it's nice. If x is literally anything except negative 1, these things cancel and they go away, and you don't have to think about them. If x equals negative 1, these things don't cancel. When x is negative 1, this is 0 over 0, and that does not cancel out. That gives you an entire mathematical catastrophe. You can't divide by 0, and that includes dividing 0 by 0. Somehow, dividing 0 by 0 is even worse than trying to divide regular numbers by 0. It is more confusing. So, we can cancel these as long as we say that x can't equal negative 1. They don't cancel if x equals negative 1. So we have to say that x can't be negative 1, and then we can cancel them, and then we're all set. And now we just have this x minus 4 over x minus 1 business, and we can kind of run through this real fast. The x-intercepts should be 4, 0. That's just what's on top. The domain restriction should be that x can't equal 1. I'm keeping this in mind, I'm just not including it in the domain restrictions, because this is going to give me a vertical asymptote. This won't. This is not an asymptote. It's something else that I will talk about more in a bit. So, x cannot equal positive 1 from this. This is my vertical asymptote. X equals 1 is my vertical asymptote. The y-intercept should be negative 4 over negative 1 is positive 4. So 0, 4. And the end behavior should be y looks like x over x, which is 1. Let's see if I can do a small graph of this while leaving all of this information visible and available. Okay, got my axes, got my info. Let's make a graph. Here's my vertical asymptote at x equals 1. Here's my horizontal asymptote at x equals -1. Y-intercept is 4. 1, 2, 3, 4. Y-intercept goes there. X-intercept is also 4. Goes right there. So right now I can probably guess that this function is going to come in from the right along this end behavior. It's going to swoop up to catch this guy and then keep going up along that vertical asymptote. On the right it's going to be doing this till it turns down to catch that asymptote, or to catch this intercept and follow the asymptote downward. So this is what the graph of x minus 4 over x minus 1 looks like. We got the intercepts, we got the asymptotes. X minus 4 over x minus 1 is not the function we started with. The function we started with was this one, which is the same as x minus 4 over x minus 1, except that x cannot equal -1. So here's how we're going to deal with that. We're going to find x equals -1. We're going to find what the graph would be right there. We're going to put a little hole in it. This indicates that there was a domain restriction here that did not impact the rest of the graph. This domain restriction creates an asymptote because when you plug in numbers really close to -1, you end up dividing by numbers that are really, really close to 0. And that's what makes it spike to infinity and negative infinity so dramatically. This domain restriction does not give us an asymptote because if you plug in numbers really, really close to -1 over here, you are dividing by numbers that are close to 0, but you're also multiplying by numbers that are close to 0, and those cancel. And they have no effect on the graph. So getting close to this -1 point from here, getting close from there, it's just like the normal graph behavior. At that point, you put a little hole to indicate the fact that that is not a good number for this function. And other than that, you're done. You graph it just like it's this function right here without this piece involved at all. And then you put a little hole. That's it. That's all there is to graphing rational functions. This has been a long and exciting ride. I hope you liked it. And this is Dave signing out.